Welcome everybody to the University of Washington's Mechanical Engineering Department seminar. This is our first talk of a series of talks on mechanical engineering for portability. This is actually one of our our chair's distinguished industrial speaker seminars today, and I'll allow our department chair, Per Reinhold, to introduce our speaker today.
Great, thanks. Yeah, today it's a great pleasure of introducing Robyn McLaughlin from Microsoft. She is the Director of Mechanical Engineering at Microsoft. And as Microsoft has transitioned from being a pure software company to, I would say, a software and device company, which requires a lot of integration, the mechanical engineering aspect has increased in importance and in value at Microsoft. So now Microsoft is a very important company for ME and our student like yourself. So there's job opportunities there. And Robyn has been, like I said, she is the Director of Mechanical Engineering at Microsoft, and she's been at Microsoft for 10 years and been involved with exciting products like Surface Pro, Surface Book, and Surface Laptop. And she graduated from Trinity University, which is a small university in Texas, San Antonio, I believe. And it's about, it's a very good university, but it's small. It's about 2,000 undergrads and 200 graduates, which I just looked up before this. And she graduated with a Bachelor of Science with a concentration in mechanical engineering. Before joining Microsoft or being recruited to Microsoft, she was at Dell for 6 years in a group that's focused on innovation of new products. So looking forward to hear you talk, Robyn. So thank you.
Yeah, I'm excited to be here. Do you want me to take over the screen share? Okay, there we go. Okay. Still relatively.
You have to use Zoom.
Yeah, I'm very used to Teams, less used to Zoom, but it's going to be okay. So I think we got it. Is everybody, you can see my presentation? Cool. So thank you, Per. As you mentioned, I'm Robyn McLaughlin. I'm the Director of Mechanical Engineering at Microsoft, Director of Mechanical Engineering at Microsoft. Today I'm going to share a little bit about my story and talk to you about product making and how I believe it to be all about designing for experiences. So to start, I'll tell you a little about myself. I'm from Austin, Texas, where most of my family still lives. I have a very large family, and we try to spend as much time as possible together when we can. Fun fact, this picture is taken in New Braunfels, Texas, where our family has gathered most years since 1935, which is pretty cool. So not that far up from the road from there is Trinity University in San Antonio, Texas, where I went to school, as Per mentioned. I arrived there without a clue of what I was going to major in. I was the 999 unknown. But I quickly learned that the engineering department got to build water balloon launchers and solar powered race cars and trusses and all kinds of fun contraptions. And I was hooked. So I knew I had always liked being a part of designing and making things, mostly woodworking with my dad and things around the house, but it seemed like a great place to start. So I went for it. After 4 years, I got my degree in engineering science, focusing on mechanical engineering. Now, what that meant was that I got to take chemical, electrical, and mechanical engineering classes all 4 years of school, but I had a heavier class load on the mechanical engineering side for my last 2 years. I worked in the machine shop all 4 years and learned a ton about prototyping. I'll admit that most of the work time I spent there was sorting drill bits and cleaning up aluminum chips, but it really instilled in me the importance of learning through making and getting your hands dirty in the shop. After my junior year, I got the opportunity to work with a graduate student at University of Houston Cullen College of Engineering through a National Science Foundation funded program called REU, Research Experience for Undergraduates. I was not sure what I wanted to do after graduation, and I thought, hey, this is either a great way to get really excited about grad school or to learn that it was not for me. Turns out it was the latter, not for me. But I was still really fortunate that I got to learn that before graduating. I still didn't know what I wanted to do, but industry seemed to be the next step. So I went ahead and started my job search. As Per mentioned, I did have multiple rejections at multiple companies, but I did land at Dell Computers in Austin, Texas. I spent over 6 years there taking on various jobs in the desktop group. My first 2 years were in sustaining, which basically meant fixing other people's designs. If there was a problem on the desktop that was already in production, we had to solve it and keep the manufacturing line going. It was a great way to start because I was able to get a glimpse of how parts were designed. Also, I got to learn what not to do. My next few years at Dell, they allowed me to design parts and be a member of the in-house design team. We made desktops from scratch. We got to work on them from all the way from the beginning, all the way to the end. And as that group evolved, we started shifting into what we called an ODM model, where we worked with a partner company to help design our products. And that became much more hands-off. I lost touch with the design aspects I'd been so passionate about, and I knew that something needed to change. But fortunately, I was able to transition within Dell into a new group. And my last year was my favorite. My last year there was my favorite. I joined an R&D group called Advanced Engineering, where we got to come up with crazy futuristic ideas in the consumer electronics world and prove out their feasibility. I worked with MEs, EEs, and software engineers, and we brought ideas to life. This combined my interests spanning from innovation and prototyping and iterating and design and everything in between, really. Unfortunately, all good things must end. And as that group was shutting down, I actually got a call from Microsoft about a young organization that was seeking MEs to help with their next innovative endeavor. It was all very secretive, and they couldn't tell me what they were working on at all. But they successfully somehow convinced me that it was going to be a group that fostered and encouraged innovation. And so I took the bait. And my husband and I moved up to Seattle, and I started working as a contractor for Microsoft, and then converted to a full-time employee after a few months. Now, my responsibilities on the first program I worked on at Microsoft was Surface Pro 1, and that included owning magnet screws, the pen, miscellaneous small components throughout the system. And when developing Surface Pro 3, I was actually able to move on to larger aspects of the program, which was exciting to me, including the motherboard and the batteries. And from there, I started leading more complex subsystems. I started managing a team of MEs. I started leading a full system. And eventually I found my way to director, where I'm now responsible for the mechanical engineering team, or at least portions of it, that develop the book product line. I would be silly if I had a slide talking about my life and not showing the most important people in it. So in addition to working for 10 years on products within Surface Pro, Studio, laptop, and book lines, my husband and I have had 2 wonderful sons, and I actually have a daughter due this August. So I am halfway through, I'm 20 weeks. So family's always been really important to me. And I've been fortunate enough to get to exercise my passion and innovation and design while also growing my family. It's been a really great mix, and I feel very I'm really glad that I've been able to do that. So I hope this gives you a good idea of where I came from, how I got here, why I love doing what I do. And so now I can dive into some of the design examples that I'm sure plenty of you are hungry for. I am going to tell you some stories from 3 different products I helped create. First, I'll talk about the development of the original Surface keyboard attachment, and then I'll talk through the Hinge design on the Surface Studio, and I'll end with what we call the Detach Module on the first Surface Book. So in my engineering classes throughout college, I was given a ton of problems to solve. Usually these problems had a general definition, a lot of constraints, and an unanswered value that I was seeking. My goal was to find that answer and show the work that got me there. I assume product making would be the similar. You want to make a computer. It should weigh this much. It should be this thick. It should have this much battery life. Now I'll go design the answer. But I quickly learned that was not even close to the case when you're trying to design something that's new and innovative and not out there. There's no recipe. There's barely even set constraints most of the time. And there definitely isn't a correct answer that you're seeking, and not just one path to get to the end. One of my favorite quotes that I relate closely to product making is this: "If I had asked people what they wanted, they would have said faster horses," attributed to Henry Ford. So before you jump to conclusions on the quote, I don't see this as consumers are dumb. I don't even see it that consumers don't have great ideas, because they do. But for me, it's more about not closing yourself off to just improving what already exists. It's more about opening yourself up to any and all possibilities and seeing where they take you. Since the beginning of Surface, we've always started each project with one thing that is going to make that product special and different from anything else in the market. Usually, that one thing has a word that we think of as a main principle or guiding light for that product. For the Surface RT and Surface Pro 1 keyboard, that word was magic. The keyboard needed to attach when you wanted it to. It needed to stay on while you use it. It needed to be able to be removed when you don't want it. And the user shouldn't have to think about any of that. No buttons, no sliders, no gimmicks, just magic. And as we started to think about how we do this, the most magical thing I had ever worked on kept coming up: magnets. There's a wonderfully awful Insane Clown Posse song called Miracles that has a line in it saying, "Effing magnets, how do they work?" And although that song is completely ridiculous, the idea that magnets are generally considered magic, it does seem pretty universal. So we made some prototypes of magnets. We learned about the general principles of magnets. We bought some off-the-shelf magnets online. This image at the top of the screen is the very first prototype we ever made, where we put some rectangular bar magnets and some circular dot magnets into both the keyboard and the device. And we tried out and just see, let's get started and see what happens. Now, we use single pole magnets, which means what you see here, each magnet has a north and a south. And so the flux is, you can see that the flux is essentially wasted in our application because it's such a large area as it travels from north to south. And we just want it to be in the area that attaches these two devices. So it gets a little bit out of hand. So we needed to research, how were we going to be more intentional about this? So we hired a magnet expert as a consultant. He came in and he started teaching us about magnets, magnetic materials, magnetic grades, certain configurations of magnets that could be used for different applications. And he taught us about all of these things. And here at the top is what's known as the Halbach array. It was actually invented in 1970. And the main purpose of this array is to contain and direct flux. So as you see, the fields don't actually have to travel as far to get from the north from one neck to the south of the next pole. And so that essentially allows them to double the flux on one side of the magnet while reducing the field to almost nothing on the opposite side. That helped us both in increasing our retention force, but also reducing the risk of having stray magnetic fields on the opposite side of the keyboard, where it could attach to jewelry or metal fibers, or even worse, erase your hotel key or credit card magnetic strips. So the other added benefit to this array is that we could put this series in both the device and the keyboard, and it made clamping great, but it also really helped with alignment. Because similar poles repel each other, this array wants to line up perfectly with its opposite match. So it was really good for our alignment. We did a combination of magnet simulations mixed with prototypes to iterate through different arrays and magnet sizes that provided a balance of clamping and alignment. This is just 3 of the many images we went through. And we landed on this array here we called it the 3C2A array, standing for 3 clamping, 2 alignment. These vertical ones served the purpose of clamping, and the horizontal ones served the purpose of alignment. we might have thought at that point that we were done, since we had gotten really good retention. It's so much better than how it started. We got really good alignment. The pogo pens that you see here were always consistently aligning every time we were attaching this device. But when we started really experiencing this prototype with the device and we started putting it in real user scenarios, we found that magnets alone were not going to do the trick. And for instance, if the keyboard is wrapped around the back of the device, the leverage was too much to overcome. The magnets would give and the keyboard would just fall off the device. So we had a lot of brainstorming sessions with a lot of engineers across the whole group, and made a whole lot more prototypes that didn't fix it. And we finally came up with the idea of fangs to serve as mechanical retention during the rotation. These features, circled on the left, mechanically bind and keep the keyboard spine from wanting to rotate, forcing only the fabric to fold backwards. So the combination of these mechanical principles mixed with the practice of really just experiencing all the different scenarios for ourselves enabled a design that in a product that we really believed was magic, but also functional. It's also worth mentioning that we got 11 different patents on just this portion of the device alone, and how we were able to create this experience in a unique way. So that was pretty cool. Okay, moving on to a very different aspect of mechanical engineering. I want to tell you about the Surface Studio Hinge. For those of you not familiar with the product, it's considered an all-in-one that contains the computing device in this lower region and a 28-inch touch and pen display in the upper section. Let me play that. Good, played. The Hinge is designed so that the user can use it as their monitor when it's up in its vertical position. They can also transition it down to a drafting table if they want to use it for sketching, and then put it right back up again to be a monitor to be productive again. The Hinge was our one thing for this product that had to set it apart from anything else in the market. To do this, we used our one word, and in this case, it was effortless. I remember the design director suggesting that this needed to be such an easy, effortless transition that his 5-year-old could come and do it without a problem, could lift this heavy monitor without a problem. He even threatened to bring her in the office a few times when our prototypes weren't quite good enough. Now, this design direction seemed really ambiguous. So we couldn't start with torque curves and force settings like you might think you might in a typical problem. We had to go back to the basics. We had to start to work through the math and free body diagrams of what might happen in different user scenarios. I'm probably made some mistakes in this, so don't judge it too much. But this sheet is from one of my engineering notebooks, and I was trying to understand what display angle would cause the device to tip over if a user applied 1 kilogram of force at the top, mimicking them closing a window or maybe even sketching at the top of the device. Now, just to get that 1 kilogram force number to start these equations, we had to design some faked prototypes and put them through user testing with pressure sensors and force gauges attached to them, and so that we could understand what a user might actually do. We had to find ways to live these experiences in order just to bring constraints to the mechanical engineering problem and be able to do the math to figure out what we needed to do. After a lot of prototyping, iterating, and even switching product teams midway through, the design finally came to an end. So I'll give you a little insight into where we landed, and I'll give you a walkthrough of the mechanism, a quick little walkthrough. So this here on the left is the display joint. This is our beautiful marketing rendering, so it doesn't have all the mechanical drawings that you might expect, but it is what you're seeing right now is a pretty intense one-directional counterbalance torsion spring designed to counteract the weight of the heavy display. It's designed to work with you as you raise it and help you, and against you as you lower it so it doesn't drop. These shiny arms, in addition to routing the cable and looking beautiful, house a 4-bar linkage design made from belts, gears, and other mechanical couplings. And it defines the relationship between the arm angle and the display angle without allowing free play or bounce. That limits the device to 1 degree of freedom, but it still enables optimized angles in desktop mode, studio mode, and everything in between. The base hinge is a compression spring-loaded cam mechanism that works with the display springs and linkage system to keep the system balanced and smooth throughout its full range of motion. After assembly in the factory, these design features are tuned in the factory with 11 unique processes that each and every system must go through before it gets boxed up to ensure that it has the perfect transition. This extreme tuning is not typical of other Surface devices we ship, but the problem was unique and difficult enough that we had to put the right processes in place to get that premium experience we wanted every customer to have. Although we were not able to start the product with a known user torque profile, one important aspect of product making is documenting the process at the end. This is partially for future development, for when we make the next one, but it's also to ensure that we have consistency in the product over time. As you can see, the final design resulted in an asymmetrical torque curve that had higher torque while lowering, like we talked about earlier, to make it feel easier to lift, and then it had higher torque while lowering to make sure it wouldn't fall down, and a lower torque while raising to make it feel easier to lift. And that's a relatively common method for fighting gravity, but probably why marketing named this the zero gravity hinge, and ultimately got us a device that the team was proud to say could actually be transitioned by a 5-year-old. The last example I'd like to walk you through is unique compared to the other two, and that it was not just mechanical engineering that had to discover and design around an experience. This is what we call the Detach Module for the Surface Book. The Surface Book is one of the higher end mobile devices that Surface makes, and it has a challenge of integrating both a CPU for compute processing and an NVIDIA GPU for graphics processing. That combination already exists in many high-end PCs on the market, but we needed one thing that was going to make ours unique. Because Surface has always been pen and touch centric, we decided we wanted this device to be something that artists and creators could use in their everyday work, but also enable mobility. Imagine a photographer who travels to LA for a photo shoot, needs to be able to real-time process their images on site, sketch on the screen while discussing with the client, and then go back to their hotel to edit all the photos and send out that night. This customer was an inspiration for an experience we wanted to enable. So we made a device that could separate from its base when you needed inking and mobility and reattach when you needed performance. Here's a video showing that removal experience, what we refer to as detach. The top tablet portion has a CPU, batteries, all the typical guts of a touch and pen enabled tablet. So it can be fully used on its own. Then when you attach it to the base, you add even more battery life and the power to run 3D CAD design, photo and video editing, or even start gaming. Now, the reason I'm walking you through this customer experience in such detail is not purely for Microsoft marketing. I really think it helps draw the picture around the one word that helped us define how we wanted this design to work: seamless. The device needed to be able to transform in a seamless way, enabling max productivity. You want to watch a movie, sketch a quick design, or show some images to a client, take the tablet off. You need to get back to being productive, attach it to the base. Designing this experience seems like a mechanical problem at first, until we realize that separating your GPU from your CPU while the GPU was being used could cause weird failures, including data loss. Not something we were willing to risk. So we quickly agreed that this needed to be an active latch or lock that asked the computer permission before releasing. Basically, we needed an actuator. And so our research began. Motors are the most typical actuators used in electronic devices, but we had to fit this in a really thin tablet. The tiniest actuator we could find was something not typically used in consumer electronics, but it seemed possible. We made a prototype using a shape memory alloy called nitinol, named for its ingredients nickel and titanium, and it worked great. We could apply a known current to it and tightly control its contraction, stop the current, and it would slowly expand back to its original shape. With the right mechanism behind it, we would be able to use this actively to release a lock and enable the top to separate from the base. Now I'll keep this video playing on loop since there's a lot to see. I think it should just keep playing. If it doesn't, I'll replay. I'll talk through how it works as you're watching it. So the picture on the right is looking at the mechanism that is housed inside the computer, except for this fang. This is part of the base that comes in and out of it. But the rest of this is housed inside the actual tablet part of the computer. The image on the left is a cross section, imagine right up through the middle essentially. So you can see how it's working, what's going on the inside of the module. Our main constraints here involved doing our best to minimize the visual disruption to the exterior of the product, making it look beautiful, while ensuring that there was absolutely zero free play or backlash that would disrupt the connector that carried all the signals between the CPU and the GPU, the top and the bottom. We needed something that could be attached easily anytime by the customer, but needed to ask permission from the computer to release. These constraints forced us to do a ton of exploring and bridging from experiences in our life as a customer, and then bring them into design possibilities and try them out. Part of our inspiration, as you can tell by the fang, came from the first thing I talked about today, the Surface Pro device and keyboard connection. We thought that magnets and fangs in conjunction would be a great start, but quickly learned that the magnets in the Pro device were not going to satisfy the force that we need to lock it in place. This is much heavier, or the alignment tolerances that we need. The pogo pins that we had in that had a lot more free play and freedom. The connector, the 80 pin connector that we used to have a CPU and GPU talk to each other, it needed extreme precision. So we basically needed to rely a lot more on the fangs in this product than we did the magnets, which is opposite of how we did on the Pro. So enter, after that, our second design inspiration, the Chinese finger trap. You can easily place your fingers I hope many of you are familiar with that. If not, you could Google it. It's something that made of typically bamboo. You can easily place your fingers inside anytime you like, but when you try to remove them, you're essentially creating a friction lock with your fingers. The harder you pull, the tighter it gets. In the design here, you see, we have a roller that is trapped between two surfaces, but it's able to roll freely if pushed or pulled. Now, as the fang gets inserted into the detach mechanism, it pushes the roller up and locks it in place with friction. If the force is applied in an attempt to pull the fang away from the bottom, from the base, it gets tighter and locks into place, essentially making it stuck. The only way it can be released is for the roller to be pulled up vertically and out of the way. This is where the nitinol, which also known as muscle wire, I refer to it as that sometimes, comes into play. And that's the blue wire that you see up here. The muscle wire is attached to a lever arm that can pull the roller up and out of its locked position. When the computer's asked permission by the user via a button on the keyboard, the signal goes to the motherboard. This is the Detach Module board, but the signal would go through this FPC to the motherboard. Excuse me. Send it a signal, ask it permission, and if it said yes, go ahead, you're not using your GPU, sends the current here, contracts the muscle wire, pulls the lever out of the way, unlocks it. Now there was a whole lot of time spent on how much current, how long do we send the current, how long does it take to cool down? How can we try to enable a space where nothing can interfere and damage the muscle wire, but also we don't restrict it and make it too hot of a little thermal area where it can retain heat. So there's definitely a lot of work beyond the mechanism you see here to make this work, but it was still a pretty intense and pretty fun problem to work through with the EE team designing these boards and the software team designing how that interaction is going to happen from customer to the actual mechanism. Now, all of these designs took an incredible amount of concept work, prototyping, iterating, testing, troubleshooting, you name it. They're a constant reminder to me of how important experiences are, real experiences are to a customer, especially nowadays when we're so closely tied to our devices. I feel proud to have a job where I can bring new ideas into the world and get to be both the designer of it and a consumer of my own work. And I think it really helps me feel connected to what I do. And it makes me appreciate the challenges I see everywhere in all different kinds of designs. It's opened my eyes to seeing a whole lot of stuff in the world, which I had never really noticed before. Now, when I'm asked advice from engineers interested in getting into this field, I encourage them to do one thing, and that is design. Find problems in your life and design a fix for it. Build it, make it better, fix it, redesign it again, and then move to another problem and do it for the same thing. I think that's where you really start to exercise that part of your brain and really start to explore and find that true innovation and that true passion. So I want to thank you all for your time and attention. I'm happy to answer any questions you have about the designs I've shown or other aspects of my experience in the product making area.
Thank you, Robyn. Yeah, you can't hear it right now, but I imagine everyone's applauding to you right now. So thank you very much. We're now going to be moving into our Q&A session here. So I see that some of us have started to ask our questions in the chat or in the Q&A or even raise your hand. It looks like we've got one from Shirar. I'll let you, maybe if you want to unmute yourself. You'd like to be able to ask your question.
Hello.
Hello, go ahead.
Thank you for a great presentation and letting me ask my question. So I have two main questions for you. The first one is about the lock mechanism that you designed for the Surface Pro, and I'm asking this question basically because my research, my master's degree, was basically on electromechanical characterization of nitinol alloys, and I'm a little bit familiar with this field. But my main question is that I assume you probably used the shape memory effect of the nitinol alloys due to the heating phenomena in them, right? So the main concern that I see here is how you address the delay in response that you receive from the nitinol alloys due to the heating, because your Surface Pro, it reacts pretty fast to this, when you want to separate the keyboard from it. But there's a delay in nitinol alloys that might be a problem in there. And my question is, did you have that problem and how you addressed that?
Yes, we definitely had that problem. There was a lot of work that went into how do we get the current to heat it up? How do we heat it up quickly? How long do we keep the heat there? How can we maintain the heat in that contained area? The best answer I can give you is that it was a big challenge and we had to go through a lot of iterations, a lot of kind of piece part design. Sometimes we always have builds where we have this big build happening where we're building the whole product and the software teams, the electrical teams, the mechanical teams are all involved. As a mechanical team, we also have a ton of sub builds where we're just building this device. And we are really just iterating through the process and figuring out, okay, when we send current, how long does it take? You know, we're sitting there with timers. How long does it take before it actually pulls up? Okay, we stop the current. How long does it take before it falls back down again? You know, we went through all that whole series of iterations and tests as we were developing this to learn that and to overcome that challenge. I think if you ask some of the engineers that design it, they might say it doesn't respond as fast as we want it to. But it was definitely an optimized process, as good as we could get it with our size constraints that we had.
Great, thank you so much.
We've got another question that was asked in the Q&A. I'll ask it for you, for the questioner. How were you able to get the strength requirement of a normal actuator from the nitinol wire?
So there was, again, prototype and iterating and equations and formulas and all that type of work. And I will start with being honest and saying, this was a long time ago. And I have actually had 2.5 babies since then. So my brain has been scrambled a few times, but I know that there was a lot of work there. We called this the lever arm. Let me go to the video. Maybe that helps a little bit more. We call this the lever arm, and we called, if I'm getting the terminology correct, we called this the rocker arm. And then we had it spring loaded, and we had to really define what is the length of the muscle wire going to be? What is the spring force going to be here? How are we going to use mechanical advantage to really be able to pull that lever out of place? And with the way that this concept of friction lock works, it actually isn't as hard as you would think it was. Like the idea of the Chinese finger trap, it feels like it's going to be impossible as you're pulling it apart, and oh my gosh, it's going to take so much force. But if you just put a little bit of force into compressing the Chinese finger trap, your finger comes out super easily. So it is a hard math and physics problem that involved a whole lot of pre-work, so that we weren't just senselessly making prototypes. But even when we do the pre-work and we say, okay, this is how much force and this is going to pull it up, and you design it, the lever only pulls up the roller halfway and it gets stuck, and we have to go back to the drawing board and redesign it, figure out what we did wrong, reiterate, go through that whole process again, spend all the money it takes to rebuild these things, go through that. Like, we definitely had to go through that here.
I have a question. Can you give us a sense of how Microsoft has changed over the last 10 years since you've been there?
Yes, it's a good question, and it's been pretty drastic. I kind of see two different realms, Surface and then Microsoft in general. In the Surface realm, when we were working on Surface Pro 1, we were like a startup. We were just trying to figure ourselves out, just trying to make something. We all came from different backgrounds, and we were learning how to work together as a team. We didn't have any real processes in place. We were figuring it all out for the first time. We made plenty of mistakes. It really took till Surface Pro 3 until we actually became profitable, and people started liking us. People outside of Seattle started showing up with Surface Pros. So there's that aspect of it, that it changed from kind of startup culture into what now is a lot more scalability, a lot more people to help do things, a lot more support. I don't have to travel to China as much as I used to, because I have teams in China. And we couldn't have been able to be a startup during COVID, because that first couple of years, we were just in China all the time, solving problems, learning about stuff, fixing things. This last year, as we've had builds for new products, we have had teams in China, brilliant mechanical engineers in China, that have been solving our problems for us and showing us that maybe we don't actually have to go to China. So the infrastructure and the scaling that's happened is pretty big. There's another big aspect that's the Microsoft aspect. Satya became CEO. He started a very long time ago. He became CEO about, I think it was maybe 5 or 6 years ago. And the culture has changed drastically since then. It's that kind of thing that you don't even totally realize that it's a problem until later. But there was the emphasis on diversity and inclusion wasn't really there, and there was a lot of kind of trying to think of how to say it. I'll just say that the culture has changed a lot, and now I feel like people want to hear each other, they want to listen to each other, they want outside perspectives and empathy. We try to be less siloed where we can from a confidentiality standpoint, and we really try to learn from each other and support a culture of learning, a culture of listening. We have inclusive behaviors, these posters with 10 inclusive behaviors that we constantly are trying to remind ourselves of listening to people and second guessing your strong reactions and not jumping to, understanding and examining your assumptions and all these things. That is an emphasis that has made a huge change, and I think enabled us to welcome a much more diverse population. And as any statistic that I fully agree with, the more diverse you are, the more options you have, the more you know how to address some of these consumer problems, the more different ideas, the more different perspectives. So it's been fantastic to get to see it go from me being the only female to now a team where there's, 8 or 9 females. It's not enough. We need some more. We need different races. We need different cultures. We need all kinds of different things, but it's made a really good progress. And I appreciate that a lot.
That's great. The questions keep rolling in. We've got 3 in the Q&A and then 2 in the chat right here. I'm gonna allow one of our questioners to unmute themselves to ask the next question.
Hi.
Hi.
I was curious about if you guys looked at the longevity of a nitinol actuator and how you kind of solved that problem.
Yeah, actually is interesting. We had an intern. His entire project was developing a tester that could help us understand that. Reliability is a huge factor in everything we do, in making premium products that are going to last over time. And we typically will lean on and use the reliability team to help us design testers and make sure that these things are lasting over time. But we were going through such rapid iteration, and there was so much complexity to just the Surface Book product that one of the engineers on our team had an intern and thought this is a perfect opportunity for him. And it was fantastic. He did a great job. He created a tester that just exercised this over and over and over again. And of course, we had to design the parameters to make sure that it was cooling down and fully relaxing before starting back up again. And we did run into some reliability problems, and we were able to FA those and find out through that tester what the life of this was going to be, and ensure that with the reliability specs we have, that it was going to meet those standards over time.
You said FA, I assume it's failure analysis?
Yes, sorry. I'm trying not to use acronyms, but it is so hard.
No, we all have our speakies, and so Microsoft Ease, if you will, or stuff like that. Great.
Yeah. When we say FA, it's failure analysis, and it's really just getting to the root of the problem, right? Just figuring out what went wrong.
Great. There's another question in the Q&A from Melissa Stossel, who's asking, on average, how long does it take from the high-level idea of the seamless keyboard experience to developing the requirements and constraints of what that means as a physical interpretation? So I guess it's like there's some soup to nuts type of ideas.
Yeah, it's a good question. It varies depending on the complexity. When we go from, we have different timelines for different products. Typically a product development from beginning concept to the end of when we're actually shipping it is somewhere between, we'll call it 18 to 24 months, depending on the product. And usually if it is something like 24 months, there's been some pretty big changes that have happened that we've had to compensate for and redirect and change. But from the actual, someone has an idea to when we have something in our hands, that can be a matter of a day, right? So not something that we would ship in our hands by any means, but make it out of cardboard, make it out of string. What we did with this particular mechanism here is there was already a nitinol prototype that existed for a different function. And we repurposed that into a form factor that is not a computer, but we pretended like it was for the sake of that. And we put it in there and showed that it could do what we did. We powered it we had a big old battery. I mean, if anybody had looked at this, I tried to find the video of that prototype because I know it exists somewhere. But the idea was basically trying to prove that this concept can be in our field and can be something that we use. And then from then on, it just grows and it just changes, and it changes a lot. And sometimes things will go through 10 or 15 iterations. Sometimes it's 150 iterations. It really depends on the complexity. So I hope, does that answer the question?
Yeah, the next question, I think this is from Santosh, but I'm not too sure, SAD. But this is for the Surface Pro Chinese finger trap. How difficult was it to deal with the variations in temperatures that could occur in a tightly packaged electronic, such as the Surface Pro? I mean, especially with like the CPU, the GPU, and how would this affect its mechanical properties?
Yeah, it definitely has a big impact. And when you can design this part at a part level and run part level testing and everything's great, and then you put it in the system and it's failing, or you put it in the system and start running a really intense CAD program or something that uses a lot more heat, or run a Windows update, something that uses a lot of heat, and it doesn't work anymore. And so we had to take system trade-offs and move the CPU to where it wasn't next to these. We had to design this black part here. We called it the super cover because it had a lot of purposes. And the original super cover didn't have holes in it. It was really just a protective thing, and it captured that heat in, and that wasn't good. And so we had to make the modification to change that. So thermal consideration was really big. For this, and we had to go through a lot of part level iterations and then a whole nother round of system level iterations to prove that we could keep this thermally stable and not have heat from the display or heat from the CPU, or variable heat that just exists in the system in general, change the behavior of this. So that was definitely a big hurdle to overcome.
The next question in the Q&A is, this is, of a personal question. They're asking, I would love to hear about your experience as being an engineer in R&D and having kids. The question, they're asking this as they're holding a 16-month-old in their hands.
Oh, I'm baby crazy right now, so I'm jealous. It's challenging. Everything in life is challenging. Having kids, probably in any form of job, is challenging. But I think the most important thing that's gotten me through, and I've gotten better with each kid. I'm more optimistic and positive about how this experience is going to go than the last two even. Having a team that really supports me. It's been our team is a family. Many of the people on our team have been with our team for the last 10 years since we started. And I've actually had the same manager for, just about 10 years, which has been pretty incredible to kind of go through this journey with the same people, the same environment, and really that support. And so when I went on parental leave the first time, it was right as we were shipping this. I went on maternity leave in September, and this was available to the world in October, which is pretty intense timeline of fixing problems and getting it out there as quickly as possible. And I was stressed out, and I thought, I don't know what, maybe I'm going to kind of pseudo work and have a baby. Maybe I'm going to figure this out. And when I had that baby, work went away. There was not even an option at that point. And if you have a 16-month-old, you can probably relate to that. Like there was no balance that was going to happen. I was going to take those 12 weeks that I had off, and they were going to be 100% dedicated to my baby. And I thought, if work goes to, if work fails, like work fails. And I came back and everything was fine. And everybody they had supported, they had gotten it into launch, everything worked great. They had started innovation and concept development on the next project. I jumped right in and had one-on-ones to kind of, where has your headspace been on this? Get me up to speed. I was excited to go back. Not everybody is, but I personally am not cut out to be a stay-at-home mom. I'm aware of that. That is a far harder job than what I do. And so I went back to work, and I got excited, and it kind of like the excitement that I got from work, I could bring from home, and the excitement I got home, I could bring into work. And like I said at the beginning, it's had its tough times, it's had its challenges, and I've had to make hard decisions. But I think my manager and everyone on my team knows my family comes first. And if it comes down to anything where there's a choice, it's a very clear choice for me. And I have a team of people that support that choice, and I support them in that choice too. And so it's worked out really well for me.
Wonderful. We got another question here. This is a question that was about from a proud Surface Book 2 user.
Yay.
Questions were about how many design iterations do you typically go through for one product? And any suggestions on reducing that number? And then there's another question about any plan to update the Surface Book design in the near future?
I can answer some of those questions. So So for a typical product, so I mentioned earlier that the system level, so building a whole functional computer, those we have very specific and very expensive engineering builds for. And there's sometimes, depending on the complexity of the program, for if we're just taking a computer and spinning the processor and updating the processor, it might take one build, maybe two builds. If we are taking it and changing some things about it, but generally keeping the form factor, it might be 2 or 3 builds. If we're going something from scratch, like Surface Book, for instance, and we're going to have this whole new concept, it's more like 3 or 4 builds. And we even kind of sneak in these, well, if we have like EV engineering verification builds, we might even sneak in an EV3B or an EV3.5 or something like that, right, along the way. So it varies depending on the complexity. But in between these builds, we are having so many, we're having, especially in COVID, a lot of kind of mini local builds here. We make prototypes, and sometimes we'll say, this prototype is not going to be functional. It's not going to have, this aspect. It's not going to have batteries, but it is going to have detach module. It is going to have the connector, and it is going to have the fan, because maybe we're, want to see how if the fan's going to get pinched or something. So we try to be really smart about how do we have these interim builds in between so that we can still just keep learning continuously and not be waiting for these big system level builds to happen. So it's kind of a constant thing.
Great. The next
questions.
No.
Was there another stream in that?
There was also I think the next Surface, but I think that might be too revealing. So you can skip that one, I imagine.
Yeah, I appreciate the question. I cannot answer that.
Yes, for stock purposes. So the other question here is, can you please elaborate a little bit on what different teams, VFX, dev, and manufacturing work on the mechanical engineering aspects of Microsoft devices and how they collaborate with each other? How do you make sure that you have had all the aspects of a product precisely designed by all these teams? So kind of bringing everybody together.
Yeah, that's maybe the hardest part of my current job anyway. It changes, it's evolved as I've gone from owning screws and magnets, which are super critical parts of the design, but stay pretty much in the mechanical world, to now responsible for a product where I have to think about every internal customer, from sourcing and what it's going to cost. DFX, which is, the acronym is designed for, and I think it's experience, but there's a lot of different functions within DFX. It's basically the mechanical engineers that help with the process and making the actual computer, integrating and putting the computer together. Manufacturing of specifically enclosures is one of our biggest areas of manufacturing, and where we have the biggest teams. We're either CNCing or stamping or die cast or whatever, these different processes, these huge enclosures that have a lot of constraints and a lot of requirements. And so we have to test the products on the line. And so we have manufacturing test engineers that design the enclosures to test the products. We have reliability engineers this is mechanical engineering I'm always talking about, right? We have reliability engineers that test and verify the quality of the product over time and help us understand, what all the different scenarios, what we can predict, what we can expect to happen. And if you lived in Siberia and you left your computer in your car overnight, is your vapor chamber thermal cooling solution going to freeze and expand and pop open and hit your battery and cause a fire, right? No is the answer, by the way. It won't, but we have to think about those things. And we have product safety engineers, right? We have mechanical engineers that span this mass spectrum of different roles that have to feed into the product to help us make it right. And when we talk about, when I talk to interns or when I'm at kind of colleges doing recruiting activities, and the assumption is, mechanical engineers design a part. It's like, no, mechanical engineers do so much more than design a part. And it's kind of incredible. And I could talk about it for another 20 minutes. I probably shouldn't, but it's a huge area that has a lot of different moving parts, and we have to spend a lot of time and energy making sure that all the contributions are heard, accounted for, and paid attention to.
Great. I think this next question might kind of fit in nicely, which is, what do you wish you had been taught, or maybe what other mechanical engineers had been taught in undergraduate, but were not? What's currently missing from new hires that you get to date? And I'm not talking about UW Huskies, because they come out completely ready.
Perfect.
Perfect. They're perfect products.
Yeah. It's a good question, and some of us have talked about this a little bit before. The ambiguity and being prepared for the ambiguity that happens in the real life. In real life, when you have kids, but in real life, when you are in this particular industry, it's kind of in the same vein as if you would have asked them they wanted faster horses. Like we don't know what we want. We want to try something that's never happened, and then we might find that it doesn't actually work at all. We need to be open to really just exploring all possibilities and not shutting something down because it seems like but that's gonna, I mean, some of the examples, if you say nitinol is going to be, you're not going to be able to control the temperature. You're not going to be able, there's some kind of things that you can easily shoot any design down. You can say why you wouldn't do things, but that's not helpful. And being able to kind of let that ambiguity thrive is really hard for most people, and especially early in career people, because you don't have that much ambiguity in school usually. And then the other thing that comes in play with that is change. Things are changing in the technology industry like you wouldn't believe. And if you are all in on, we'll just use the generic use of USB-A, and you want USB-A, and that's what you design in, and USB-A is a certain size, and it has a certain electrical connection and a cabling, and everything is designed for USB-A. And then all of a sudden the industry, you realize everything's changing. By the time we release this product, USB-C is going to be what people care about. We have to change. Like, that's hard. It might seem like a simple, okay, just swap out the connector. It's way more complicated than that. It impacts your motherboard, it impacts your enclosures, it impacts the cabling, it impacts all the components around it. Maybe it's maybe the thing you're having to change is a hotter component, or something that is dynamic and can make it even harder, and you have to have more reliability testing. So being able to live and be comfortable in ambiguity and just trying new things and being open to that, and then being able to change at a pretty rapid pace, those are things that are hard to find in anyone, not just college hires. A lot of industry hires, we have that problem. But I feel like some of the best engineers that I've worked with and in Surface over time have really done a good job of grasping those two things.
Thank you. I know we've kept you for a whole hour here. I want to say thank you so much. I think there's a lot more other questions, I imagine, in the chat and other people's minds, but I think I want again say thank you for presenting for us today, and it was a fabulous talk and a fabulous Q&A as well.
Thank you.
Yeah, thank you very much.
Thanks for having me. It's great. Those are good questions. Very good questions. Thank you.